So half-life, we need to understand what half-life means. We need to be able to interpret a graph to show half-life, because half-life is normally shown on graphs. And maybe towards the end we'll do a little bit of a calculation to do with half-life, so you can see how it's applied before we look at something called carbon dating. So why does radioactivity decrease over time? If you imagine this source here, if you were looking at the count rate, this is showing 4,000. So if I just start off this little animation, if we imagine over time, then this count rate would drop. If you actually had a Geiger counter connected to a rate meter which shows the radioactivity coming from the source, if we noted it over time, it started at 4,000, and after however many hours or whatever we were timing, you would notice that it would start to drop. So I wonder why. The question is, why does this happen? You've got to try and think in terms of the atoms inside the radioactive source. So if we sort of zoom in onto the radioactive source, here we go. Imagine all the individual atoms, then there's a chance that at any moment any one of them might decay, whether it will be alpha or beta, like we've looked at. But that chance is equal between all of them. So out of, I think we've got 30, so out of the total 30, in the first 10 seconds here, 5 atoms have decayed. So we started off with 30, and after 10 seconds, 5 have decayed, leaving us with just 25 left. If we run the clock again for another 10 seconds, then there's the chance that some will decay again. There's the same chance for each one. But because there's less of them, you'd probably be happy to accept that less will decay. We only had 25 to start with, so now we've only got 4 that decay. So in another 10 seconds, 4 have decayed. So if we run it again for another 10 seconds, this time we've only got 21 left. Again, the same chance that any of them can decay, but because there's less of them, we probably are going to have less decay. And now if we let it finish, we've only had 3 decayed. So you can sort of continue this idea on, and you sort of will see that why over time the number of atoms decaying at a given time decreases, as it said, so the amount of radiation detected also decreases. Okay, so here we have another animation. These are all the atoms that currently, I haven't started them off to allow them to decay, so if I quickly start them off, allow them to decay, you can see that straight away some of them decay, and over time it sort of starts to, there's less and less left, because the rate at which they decay, even though the chance of each one decaying is the same, the rate at which they decay falls off. If we imagine plotting a graph of this, let's just have a quick look at a graph, we would see that over time the activity is falling. And the key idea with half-life is that the half-life is the time it takes for the activity to drop to half of its original value. If we look at this next animation, this gives us some numbers on it. So if we start it off, so imagine the same experiment. If we plot a graph of the activity of a radioactive sample against time, so time goes on the x-axis and the activity goes on the y-axis, you can easily see from what we've looked at that you would have a graph that shows a shape like this. And to work out the half-life, what would you do? You would say, well, I started off with 80 counts, so if I halve 80, the time it takes for me to get from 80 down to 40 is 2 minutes according to this graph. So to get from 80 to 40, we're down to 2 minutes. You could repeat that again. Let's look at the time it takes to get from 40 to 20. Have a look at that. And 40 down to 20 is taking another 2 minutes. So it goes from 2 minutes to 4 minutes, and this animation continues. 20 down to 10 takes another 2 minutes. So you would say the radioactive half-life of this sample is 2 minutes. So in summary, in a radioactive substance, unstable atoms decay. That happens by alpha or beta decay, as we've talked about, and after they decay, they sort of eventually they may become stable. The half-life of a radioactive sample is the time it takes for the number of nuclei of the isotope in a sample to halve, or it's the time it takes for the activity of a sample to halve. We can use this to work out some little mini calculations. If we imagine the example, a radioactive isotope has a half-life of 15 hours. A sealed tube contains 8 milligrams of the substance. What mass of the substance is in the tube 15 hours later? So we're told that the half-life is 15 hours. So 15 hours is one half-life. So we've got to halve the amount left. So the amount left is going to be half of 8. So it'll be 4 milligrams. And applying the same idea, 45 hours later, so the maths in your head, you need to think how many half-lives are in 45 hours. And you should be able to work out there are 3 half-lives because there are 3 15s in 45. So the first half-life, 8, drops to 4. The second half-life, 4, drops to 2, it halves. And the third half-life, 2, will drop to 1. So there is 1 milligram left. The big use of half-life is in something called carbon dating. You need to have an idea of what this carbon dating means. So if we just run through this animation, the whole idea is that carbon, there's lots of carbon in the atmosphere naturally, and some of it is going to be radioactive. The reason it becomes radioactive is because of cosmic rays in space interacting with the nuclei, making it radioactive. So we have carbon-14 is formed by cosmic rays interacting with nitrogen, and some of the carbon will become carbon-14, some will remain another isotope of carbon, carbon-12, so you'll have a mixture of both. They're made at the same rate, so you've got naturally a proportion of carbon-14 and a proportion of carbon-12, and this remains fairly constant. Now what happens next is that any carbon tends to end up as carbon dioxide, and from our biology we know that plants, any living plants take in carbon dioxide. So in any plant there's going to be a proportion of radioactive carbon dioxide, carbon-14, as part of the carbon. And you can see here from our little animation we've got someone coming along and eating the berries or eating the plants. Now that means, if you follow what's happened, is that there's an element of the plants that's radioactive, and there's also an element of our friend that's been eating them that will be radioactive. So throughout the plant's life and throughout the human's life, they are both going to be radioactive. But unfortunately, at the point where the plant dies, or in our case here, our human, our caveman or bogman dies, there's going to then be a change in the amount of carbon-14. The carbon-14 that decays will not be replaced, so the amount of carbon-14 will begin to fall. And what you can do from that, knowing the half-life of carbon-14, and the half-life of carbon-14 is about 5,700 years, you can look at the amount of carbon-14 that's left in a sample, and you can compare it to the proportion of other types of carbon, and you can work out how old the thing is that used to be alive. So carbon dating is brilliant for dating things that used to be alive. This can either be something that was living like a human or a dinosaur, or it could also be a cloth made of some kind of plant. So very, very useful, and you'll often see questions and applications of this in the exam.